Assalamualaikum dan salam sejahtera. So welcome back to our online class. So today we will look into the concept and operation of the induction motor. So how the rotor rotate in the stator. Okay, for the concept and operation of a three-phase induction motor, so we have the stator, which is the stationary. Then we have the rotor, which is the moving part. Okay, let's say we have a three-phase supply. Okay, then three-phase supply is connected to the stator winding. So when the three-phase supply is connected, it will produce the current will flow in the coil or winding. So therefore it will induce three-phase flux in the stator. So it will produce the electromagnetic flux, electromagnetic field in the stator. Okay, so this electromagnetic field will rotate at the synchronous speed. That's why we call it as the rotating magnetic field. Okay, the rotating magnetic field or rotating flux in the stator is equal to the synchronous speed. So Ns is referred to the rotating magnetic field in the stator. So the formula is equal to 120 times frequency over P. P is a number of pole. In terms of how the rotor can rotate in the stator. Okay, previously we talked about the rotating magnetic field in the stator. Okay, stator is not moving. Stator is a static. Okay, how the rotor can rotate? Okay, so the answer is a true torque producing mechanism. Okay, so let's say when we have a three-phase stator winding, then it is connected to the three-phase supply. So three-phase current will flow in the winding. Then the stator is energized and it will produce the rotating magnetic field. Okay, so this rotating magnetic field is equal to synchronous speed Ns. Okay, effect of that. Okay, the rotating flux or rotating magnetic field is produced in the A gap. Okay, at the same time, the coil or winding in the rotor is induced due to the rotating magnetic field in the stator. Okay, so because of the flux cutting, so it will produce the induced voltage or back EMF in the rotor winding. Okay, therefore the induced voltage produce the rotor current if the rotor circuit is closed. Okay, if the winding and the rotor is closed, okay, or terminated. So the rotor current interact with the flux, so it will produce the torque. So the rotor rotates in the direction of the rotating flux. So the concept of the induction motor is similar to the concept of a transformer. Why we call it as an induction motor? Because the induced current flow in the secondary or in the rotor because of the rotating magnetic field. Okay, so we produce the induction voltage, and then the interaction between the voltage in the rotor and also the stator, so it will produce the torque. Okay, slip and rotor speed. So what is slip? Okay, the rotor speed of an induction machine is different from the speed of rotating magnetic field. The rotating magnetic field is a synchronous speed, so the percent percent difference between the synchronous speed and rotor speed is we call it as a slip. So the formula is S equal to slip equal to synchronous speed minus rotor speed over synchronous speed. So we can calculate the S, the slip. Okay. Basically, the slip, the percent difference between the rotor slip, between the rotor speed and also the synchronous speed is very small. So slip equal to between 0.01 to 0.05, which is very small. Okay, however, cannot neglect S. So in the calculation, we must consider S slip in our calculation. Okay, next is a rotor frequency. So the rotor frequency is different between the frequency of the incoming. Okay, to calculate the rotor frequency, we can use the formula Fr. Fr is represented the rotor frequency equal to Sf. S is the slip and F is the frequency of the incoming supply. So we can calculate the rotor frequency in the induction motor.
Induction motors are the most commonly used electrical machines. They are cheaper, rugged, and easier to maintain compared to other alternatives. In this video, we will learn the working of a three-phase squirrel cage induction motor. It has two main parts, stator and rotor. Stator is a stationary part, and rotor is the rotating part. Stator is made by stacking thin-slotted, highly permeable steel laminations inside a steel or cast iron frame. Winding passes through slots of stator. When a three-phase AC current passes through it, something very interesting happens. It produces a rotating magnetic field. To understand this phenomenon much better, consider a simplified three-phase winding with just 3 coils. A wire carrying current produces magnetic field around it. Now, for this special arrangement, magnetic field produced by three-phase AC current will be as shown at a particular instant. With variation in AC current, magnetic field takes a different orientation as shown. From these 3 positions, it's clear that it's like a magnetic field of uniform strength rotating. The speed of rotation of a magnetic field is known as synchronous speed. Assume you're putting a closed conductor inside it. Since the magnetic field is fluctuating, an EMF will be induced in the loop according to Faraday's law. The EMF will produce a current through the loop. So, the situation has become like a current-carrying loop is situated in a magnetic field. This will produce magnetic force in loop, according to Lorentz law. So, the loop will start rotating. A similar phenomenon happens inside an induction motor also. Here, instead of a simple loop, something very similar to a squirrel cage is used. Three-phase AC current passing through stator winding produces a rotating magnetic field. So, as in the previous case, current will be induced in bars of squirrel cage, which is shortened by end rings, and will start rotating. That's why it's called an induction motor. Electricity is inducted in the rotor by magnetic induction rather than direct electric connection. To aid such electromagnetic induction, insulated iron core lamina are packed inside the rotor. Such small slices of iron make sure that eddy current losses are minimum. This is another big advantage of a three-phase induction motor. It is inherently self-starting. So, you can see here that both magnetic field and rotor are rotating. But at what speed will the rotor rotate? To obtain this answer, let's consider different cases. Consider a case where the rotor speed is the same as the magnetic field speed. Since both are rotating at the same speed, the rotating loop will always experience constant magnetic field. So, there won't be any induced EMF and current. This means zero force on rotor bars. So, the rotors will gradually slow down. But as it slows down, rotor loops will experience a varying magnetic field. So, induced current and force will rise again. And the rotor will speed up. In short, the rotor will never be able to catch up with the speed of the magnetic field. It rotates at a specific speed, which is slightly less than synchronous speed. The difference between synchronous and rotor speed is known as slip. Rotational mechanical power is transferred through a power shaft. In short, in an induction motor, electrical energy is entered via stator and output from motor. Mechanical rotation is received from rotor. Energy loss during motor operation is dissipated as heat. So, a fan at the other end helps in cooling down the motor. Hope you got a good introduction on the working of induction motors. Thank you.